So when you say open loop, what is open loop? Open loop is Nabu bag. There's nothing there. Huh? There's no, just you move, it comes back. Move, it comes back. Huh? Volume control open loop. You are giving a volume, it's coming back. You see a pressure volume is giving 300, 300, you bronchospasm, what happens? Nothing. 300, 300, 300, 300, 300. Closed loop is kind of knowledge-based system. It's kind of knowledge-based system where what you're doing inside, the ventilator looks at it and then gives you a feedback. Okay, boss, your plateau pressures are going up, or your pressures are going up, or your volumes are too high, and it gets back to you. That's a closed loop. Huh? Closed loop and open loop. Okay?
So this occurs from breath to breath in ASV. It is an automatic. There is automatic adjustment of settings according to this closed loop mechanism, and it optimizes the work-out breathing. The entire principle is to minimize the work-out breathing. That is what we are concerned about. So that it does by providing a specific minute ventilation, optimal target to have the least possible work-out breathing, and it is based on the patient's requirement through the closed loop mechanism. So what are the operating principles of this mode? So this mode is a pressure, it controls the pressure with pressure control with minute volume guarantee. That is based upon two equations. One is the Otis equation and another is the Mead equation. These equations were in 1950. That they state that to give a level of alveolar ventilation, there is a particular RR which is required to achieve a lower work of breathing. Okay. This is the Otis equation, wherein the RC is the time constant that is derived based upon the resistance and the compliance of the patient. The dead space is calculated 2.2 into ideal body weight of the 2.2 ml into the ideal body weight of the patient, and A is the constant for the sinusoidal fluid. So as we can see in this graph, our target is the optimal RR, which is point C. Optimal RR where there is minimal work-out breathing. Now point A, where you can see it clearly shows that in order to maintain alveolar ventilation with very low respiratory rate, it is needed, we need to use larger, means the patient uses larger tidal volumes, which implies that there will be high work-out breathing. On the other hand, if you see point B, which shows that the high amount of muscular effort is required to maintain adequate alveolar ventilation at high respiratory rate in an attempt to overcome the resistance to flow. At point C, we have to, the patient has to overcome the resistance to the flow. On the other hand, at point A, the patient has to overcome the elastic forces, pulmonary and the thoracic forces. However, there is an optimal RR which is least costly in terms of work-out breathing, which is point C. Now, this is how the mode calculates.
So let's go back to that. So you want to understand here is that, see, when you are actually going on point A, what are you doing? You are giving volume to inflate the lung.
Yes.
Here, you are giving volume to inflate the lung. So how much work he requires the patient? This patient requires work to inflate the chest wall and inflate the lung.
Yes.
He has to do both. He has to inflate the wall, the lung, as well as the chest wall. That's why the volumes required are high. That's why the work is very high. The work is required. Similarly, when he comes down here, since the volumes are low, since the volumes are low, he will need to breathe heavily. Now here the effort over here is to breathe in, breathe out, breathe in, breathe out, breathe out, breathe out faster. So again the work of breathing is very high here. Either at a high respiratory rate with a low tidal volume, or a high tidal volume with a low respiratory rate. Have you understood this? So the work of breathing is very high here, work of breathing is very high here, and probably the optimal work of breathing is somewhere around here, which is a good judge between tidal volumes and the respiratory rate.
Yes.
Simple? Huh?
Yes.
So that's the entire thing. How do I get it here?
Yeah.
Okay?
So once we put our ideal body weight in our ventilator, and there are certain settings which we set in an ASV mode, which is the percentage of the minute ventilation, the peak, the FI. So based upon the through the closed loop mechanism, it judges the respiratory mechanics as in the compliance and the resistance, and it puts into the Otis equation. From there, it tries to come to a safer tidal volume and the respiratory rate, so that the minute ventilation is achieved. And by it also adjusts the IE ratio and the inspiratory pressure. So it calculates everything through these equations and comes to an optimal R. So this is the safety window, which means which at which the optimal ventilation is happening. This is the normal mechanics, like the square shape, where the rate and the tidal volume is optimal. In a restrictive disease, where the compliance is low, so it sets low and a wide rectangle shape, as in the respiratory rate and tidal volume is adjusted according to the mechanics. Similarly, in obstructive disease also, it sets a higher tidal volume and a low respiratory rate.
So what is happening here is, if you look at it now, the ventilator is knowledge based.
Yes.
So what is it doing? It is actually figuring out the compliance. It is figuring out the resistance. It is doing all those things. So it is understanding obstructive airway disease. It is understanding restrictive airway disease. It is understanding all those things. So if it was normal, this is how it is.
Yes.
It was normal. So it will ventilate this patient inside this, but there will be a plus sign on the ventilator, which will ventilate the patient inside this box. So somehow the plus goes out here. Very soon you will see all the changes happening and the plus coming back inside this. Okay, so you don't have to do anything. आपको कुछ नहीं करना. समझा रहे हैं? तो otherwise what I would do if this patient is breathing say fast, because he is having compliance issues. So if he is breathing fast, he is somewhere around here, the outer box. Right? So what this ventilator will do? It will try to slowly increase the pressures, increase the volumes, so it gets a little bit more volume. So his RR will come down, and this plus sign will come into this. So it does this on a breath-to-breath basis. You are understanding? So the plus comes inside of PP. So not a single breath is out of this issue. That's the point. One breath may come, so again everything has to become normal again. That is the intelligent part of the ventilation. So if you have a obstructive airway, then the entire thing will be like this. Sure. So this is obstructive, no? Obstructive will be like this, where your tidal volume should be higher. If you take a call on giving more tidal volume, but reducing the RR, because obstructive airway disease, expiratory airflow has to be much higher. Expiration should be much longer. So what it does, it actually gives you lower respiratory rates and higher tidal volumes. So when you do a COPD lung ventilation, you want the volumes to be slightly higher, and you want the RR to be lower. So it is actually doing that. Similarly, in a restrictive pattern, what it is doing is this way. It is actually increasing the RR. So an ARDS patient will be in this window. An ARDS patient like this, and you don't decide that. The ventilator decides that, because ventilator is calculating compliance. So it will see the compliance is 10. So once it sees the compliance is 10 on a regular basis, it will start figuring out that this is probably ARDS. This is probably not okay. It will do that. It will figure out that ARDS, this is not something I must look at. It will quickly come to this. Meanwhile, if a patient achanak se has bronchospasm, and he's on a tremendous bronchospasm, then what will happen? It will again go back. So it will go back to that obstructive window, and it will try to actually compensate for that. It will not allow this patient to be in a wrong zone. For example, you have an ARDS. Okay, you have an ARDS. So let's put the ARDS window. So this is ARDS. Okay, you have an ARDS window there. If this patient you are managing without this machine, say for example, what do you have to do? You can manage. No, we are managing. How do you manage? So we are managing how we have kept a tidal volume of 350, say 300 or 350. Okay, 350. But if you are यार ये 80 to बराबर नहीं हो रहा है. हमने 350 को 345 कर दिया या 400 कर दिया. Now over a period of time, what has happened is this patient, as patients, is constantly breathing, and they start taking tidal volumes that are much higher. It will not allow it to do that.
Okay, yeah.
It will
change the pressure.
It will get it back. Similarly, if you are doing all the adjustments, if the compliance has worsened further, and now this has gone out of the window, it has worsened further, it will actually try to get it back here by changing the pressures in such a way, because essentially it's pressure control. Essentially it's pressure control. So what is going to happen is it will change the pressures in such a way that you are no longer subjecting this patient to such a high tidal volume. So at any given moment, if you switch on the ventilator that is working there and you press tidal volume, you will not see it going more than 6 ml per kilogram.
Yes.
You will not see it going more than 6 ml per kilogram. You have to do everything possible to keep it less than 6 ml per kilogram.
Yes.
You understanding? Huh? You understood this?
This is how, like so I said, this is how it works. When it is outside the box, it will do the changes. Like if it's in this side, it will increase the pressure, increase the respiratory rate to come into the target. Okay. So if the tidal volume increases, it will decrease the pressure and increase the respiratory rate. Similarly, if the respiratory rate increases, it will increase the pressures to achieve a increased tidal volume and decrease the respiratory rate to come into the safety window. So what is the goal of this mode? It is to have an effective alveolar ventilation, minimize the work of breathing, and optimal ventilative pattern in order to reduce the complications like volume trauma, viral trauma, air traffic. So what we set, what are the control parameters? Minute ventilation, PEEP and FIT. The minute
Okay, you put the video please. Yeah, go ahead.
So minute ventilation range variability is from 25 to 350% up to we can set. The normal setting in a normal lung is 100 to 110%. If it's a restrictive disease, we want a higher minute ventilation. So up to 130 we can do. 110 to 130%. And in obstructive, we'll set a comparatively lower minute ventilation up to 90%.
So if you have a patient who's coming in from outside with ARDS and pneumonia, you set at 130%.
Yes.
It's as simple as that.
Yes.
If it's COPD, you come to 90%.
90%.
That's how it is.
Now how we initiate? We first of all set the gender and the height. Okay. The machine estimates the predicted body weight with the algorithm, with the nomogram, and then it calculates the dead space 2.2 ml of the ideal body weight. We also set the flow trigger to 2 liter per minute, tube resistance as a compensation to 100%. We set the high pressure lung limit and the expiratory trigger sensitivity, 25% in a restrictive disease and 40% in obstructive disease. Now how it works, it will then set the use its algorithm to calculate the respiratory rate and tidal volume. Then it gives a test breath around between 10 to 15 of the ideal body weight at the rate of between 10 to 15 of the ideal body weight. And it will calculate, it will see the respiratory mechanics, the resistance and the compliance to calculate the RC expiration, and spontaneous activity is estimated from breath to breath of the patient. And then it will do the murmurs to bring the respiratory and tidal volume in the safety window. Now in a passive mode, it works like a pressure control mode, and in an active mode, when the patient is breathing, it will switch between the SIV mode and the PSV mode, okay, to achieve the target minute ventilation. Then wean. When we want to, we can use this ventilation from start to end. In whether the patient is spontaneously breathing, whether the patient is paralyzed, we can use till the weaning. We can use this way. So the minute ventilation now we have to lower in steps of 10% with frequent assessment, and the support can be tapered up to 25%. Now the ASV parameters are considered to be minimal when all breaths are spontaneous and the inspiratory pressure is less than 8 cm above the baseline. Once the minimal parameters are achieved, the SBT, it keeps on giving the SBT, and then we can extubate the patient accordingly.
You understand, no? So you start, say for example, to take the journey of a patient. Now you come from, say, an operation theatre, or you come from the casualty. You set the minute ventilation as 130%. Now you started at that, and then you look at then you forget. You all you have to do is adjust the oxygenation. Okay, you just put them, you adjust the oxygenation, everything else it takes care of. So PEEP and FiO2 is all that you set. You set the PEEP and you set the FiO2. Right? To set the PEEP and the FiO2, this particular bazooka ventilator also has a PV curve, PV tool. You can actually figure out what the optimal PEEP is. It doesn't have the FRC. Each of these ventilators have got some yes, some no, it's like that. But this has got the PV loop. So you, sometime later, if that patient is on top, I can show you how to do the PV loop on that particular ventilator. Okay? I'll show you on that ventilator how to do the PV loop. Okay? So in this ventilator, say this patient has come in, you put the, for example, the patient on top who's on ASV now. Okay? So we put it on 120%. We put on 130% and then we leave it, forget it. Okay? Now there is a white box where you'll see whether everything parameters are in the right place, whether these pluses are in the right place, whether the plus is right inside the box that we talked about. Okay? You will look at that. Okay? And then subsequently, if it is in that place, it will you are comfortable that everything is looking well. Now 3 days have passed, 4 days have passed. Patients all his process is getting better and better and better. He starts breathing on the own also. You don't have to change the ventilator from this to pressure support. You don't have auto trigger. You don't have all those things. Asynchrony comes down because you don't have to do anything. Otherwise, it's asynchrony. Otherwise, say if you're in volume control and this patient starts breathing, what is going to happen? If the volume control patient starts breathing, every breath will be assisted with the volume. So if the patient is breathing at 10, you will get 10 breaths. If you have said 10 milligrams. If you said 20, you will still get 220. 20 full breaths you will get on assist control. So his minute ventilation will go up, his volumes will go up. He will on the whole become asynchronous. His diaphragm is in a different league. His neural respiratory is in a different league. So a number of asynchronies would start coming in. What happens over here? Without you knowing only, the ventilator picks up that this patient is taking a breath. And rather than actually giving this large tidal volume otherwise that he would receive, it still ventilates him in that box. So he gets a low tidal volume, he gets adequate pressure, and he's in that box. Now as time goes, slowly there, in that box you will see his spontaneous was only 20% spontaneous breathing. Then it becomes 40%, and then it becomes 100%. So once it becomes 100% on that breathing pattern, we now know that okay, he's breathing full. Now you look at the pressure on that level. If the pressure support has come to A, that is what your CPAP is. The pressure support of A, B, जो minimum set किया हुआ है, and if fully spontaneous, he's undergone an SBT. The ventilator automatically go to an SBT and will tell you that okay, 1 hour has been done already.
Yes.
So in effect, weaning time will come down. In effect, weaning time will come down. You'll know. Otherwise, we don't know. Unless you stand at the ventilator, spend time, you will not know. Okay, you understood the entire thing?
So advantages are that it's a versatile. Patient can ventilate any patient and do it in a safe manner. Prevent tachypnea, autocreep and dead space, like it will always keep it in the box. And less operator dependent, less need for operator involvement. Decreases the time on minute mechanical ventilation and adjusts the patient according to its inspiratory effort. The disadvantages are it cannot directly program the tidal volume, respiratory rate and IU ratio. Limited pediatric experience. Algorithm tends to ventilate with low tidal volume and high respiratory rate. Only available in Hamilton method.
So that's what happened in one of our patients. What happened to that patient that we were on? He started breathing at a higher RR.
Yes.
The patient is ventilating at a higher RR. Okay, but you must understand that a higher RR is not as difficult than a higher tidal volume.
Yes.
The pathology is different. You understand? The patient is breathing fast. His ventilator is breathing with the patient fast, but it's not giving high tidal volumes. So it is still comfortable. It is still okay. You treat the cause. The cause may have been gone into a restrictive pattern, fluid has increased, something like that. So it's going into the fast RR to reduce the tidal volumes.
Yes.
Are you understanding? It is tidal volume. Compliance is worsened. That is what occurred. Compliance worsened. Patient probably collapsed because he was on the ventilator. Compliance would have worsened. That's why he became fast. Why did he become fast? Because you understand the reason why he became fast, this particular patient, because we had extubated him. After extubation, what is going to happen? His PEEP is gone.
Yes.
So there has been a collapse in the lung, and that collapse in the lung has caused the compliance to actually reduce.
Yes.
Since the compliance has gone down, that box has changed from normal box to a smaller box, a restrictive disease, because it's restrictive anymore, it's ARDS type. So it becomes restrictive. So the compliance has come down. What is the ventilator doing? I am not going to give large tidal volumes.
More RR.
That's why it increases RR. You understand? So the only parameter that in this ventilator that you probably may have a problem with is the PEEP. And to get that right, that ventilator actually has a transfer pressure pod.
Yes.
To get that right. Okay, so at the end of the day, when we monitor esophageal pressures in our ICU, okay, we used an esophageal catheter. We get a waveform. This ventilator, when you attach that also, this becomes a complete set. You get even the pressures. The only thing that you will not get, and you'll have to estimate objectively, is the regional overdistension. You have to estimate. You have to think that the compliance is going down, so this might be overdistension, which in addition to this ventilator will make it a complete set. If there is electrical impedance tomography that we've been doing, what will we realize? That this PEEP is adequate or not.
Yes.
Or whether it's causing overdistension or not. You got the point. So if this is coupled with an EIT, it will become like the best thing in the world to ventilate with. Full AI, full artificial intelligence, nothing to be worried. Full knowledge base. You got the point. It will become perfect. So imagine we have this ASV and then we are using the EIT belt. It becomes a combination because we are using FRC, we are using EIT, we are using transmitted pressure, and we are getting everything. Here when you put the transmitted pressure, you just don't get just the waveform of the esophageal manometer on this ventilator. You actually get the transpulmonary pressure. So all that you need to do is increase the PEEP so that the transpulmonary pressure and the PEEP and the esophageal pressure coincide to each other. When that occurs, you have done the right thing. When that occurs, you have done the right thing. It's so simple. PEEP को हम लोग जब भी करते हैं transpulmonary pressure, what are we doing? We're calculating that P inspiration and that minus PEEP. We're doing all that, right? We're doing the calculation, we're finding transpulmonary pressure, we're seeing what is happening, and then we're going ahead, right? In this, you don't need to do all those calculations. You just increase the PEEP and you'll see it coincide. So at the end of the day, it becomes a complete ventilator. But unfortunately, this particular technology is there only with Hamilton for the last 10 years now, 10, 12 years. It's not gone to any other ventilator. No other company has it, and it will remain with them for the next 15 more years. Okay, but you by now you would have understood why ASV is too good. Now let's understand a little bit more from Akash. Come. You all know Akash is with us. Now he's speaking to you from Hamilton.